Hello there and welcome to the Sleepy Science channel. I'm so glad you found your way here tonight. Maybe you had a long day, or maybe you're the kind of person who likes falling asleep to the quiet wonder of space and science, rather than counting sheep or staring at the ceiling. Either way, tonight's journey is for you. You've got nothing to do but rest. Let your mind relax, your breathing slow and your body grow light, as if the Earth's pull has softened just a little. Because tonight, we're not simply looking up at the moon. We're drifting through its history, from the violent collision that gave it birth, to the footprints left by astronauts half a century ago, a companion that has watched over Earth for more than 4.5 billion years, shaping our tides, stabilizing our seasons, and lighting our nights with borrowed light from the sun. But beneath its familiar glow lie secrets, ancient impacts, volcanic plains, frozen water in shadowed craters, and a slow dance with Earth that continues to this day. We'll travel gently from its fiery formation to its cratered surface, from the pull it exerts on our oceans to the missions that carried humans to its dusty soil. You'll hear of magma oceans and moonquakes, of tidal forces and phases, and the quiet story of a world still shaping our own. Some of what you hear tonight may surprise you, or at the very least spark some curiosity as you drift off to sleep. And just before we begin, if these calm, curious explorations help you unwind or give you a quiet way to end your day, consider liking and subscribing to the channel. It helps others find their way here too, one sleepy soul at a time. Let's begin. The moon's violent birth. The moon was not always there. 4.5 billion years ago, when Earth was still young and molten, gathering mass from the swirling debris of the early solar system, something extraordinary happened. A collision so violent, so energetic, that it fundamentally changed the fate of our planet and gave birth to the companion we see in the night sky today. This is the story told by the giant impact hypothesis, the leading scientific explanation for how the moon formed. It begins with a Mars-sized protoplanet, a world still taking shape in the chaotic neighborhood of the inner solar system. Scientists call this body Theia, named after the Greek Titan who gave birth to Selene, the goddess of the moon. For millions of years, Theia may have orbited the Sun in a relatively stable position, possibly at one of the Lagrange points in Earth's orbit, places where gravitational forces create natural parking spots for celestial bodies. But gravitational dynamics are never truly stable for long. Perhaps perturbed by the growing influence of Jupiter and the other giant planets, or simply nudged by the countless interactions between protoplanets jostling for space, Theia's orbit gradually shifted. Eventually, about 4.4 to 445 billion years ago, roughly 100 million years after the solar system began to form, the inevitable happened. Theia and the proto-Earth collided. The impact was not a head-on collision at maximum velocity. Computer simulations suggest that Theia struck Earth at an oblique angle, perhaps at about 4 kilometers per second. This was still fast enough to be catastrophic. The energy released was beyond comprehension. The collision melted vast portions of both bodies, creating a global magma ocean on Earth that may have extended hundreds of kilometers deep. The temperatures were so extreme that rock vaporized and much of the material from both worlds was flung into space. Some of this debris fell back to Earth. Some escaped into space entirely. But a significant portion remained in orbit, forming a disk of molten rock, gas, and vaporized material around the young Earth. This debris disk, sometimes called a lunar synestia, was a churning, glowing ring of material that must have been spectacular to behold, had there been anyone to witness it. Over time measured in thousands of years rather than millions, this disk began to cool and condense. The debris clumped together through the same process of accretion that built the planets themselves. Larger fragments attracted smaller ones. The disk gradually coalesced into a single body, and the moon was born. This violent origin explains many of the moon's unique characteristics. The impact stripped away much of the lighter outer layers of both Earth and Theia, material that was rich in silicates but poor in iron. This is why the moon has such a small iron core compared to Earth, less than 5% of its radius. The moon's density at 3.34 grams per cubic centimeter is noticeably lower than Earth's 4.2 grams per cubic centimeter, reflecting this difference in composition. The immense heat of the impact also explains why the moon is depleted in volatile elements, substances that evaporate at relatively low temperatures. Water, sodium, potassium, and other volatile compounds were largely vaporized during the collision. The moon's weaker gravity was unable to recapture these gases as they escaped into space, leaving the moon essentially dry and depleted in these elements. Evidence for the giant impact hypothesis comes from multiple sources, but perhaps the most compelling is the chemical similarity between Earth and moon rocks. When Apollo astronauts brought back lunar samples, scientists discovered that the isotopic ratios of oxygen and other elements in lunar rocks were nearly identical to those found in terrestrial rocks. This was puzzling at first because if the moon had formed elsewhere in the solar system and been captured by Earth's gravity, or if it had simply condensed from the same cloud of material alongside Earth without a collision, the isotopic signatures would likely be different. The giant impact hypothesis solves this puzzle. If the moon formed from a mixture of Earth and Theia material, and if Theia itself had formed in the same region of the solar system as Earth, then the similar isotopic composition makes sense. More recent studies suggest that the impact may have been more direct than originally thought, leading to even more thorough mixing of the two parent bodies. Analysis of lunar samples published in 2016 showed that the impact might have caused complete fragmentation and mixing of both Theia and proto-Earth, which would explain why Earth and moon rocks are so remarkably similar. The collision was not just a glancing blow that threw off some debris. It was a catastrophic merger that melted and mixed both worlds before they separated again. This was not the only giant impact Earth experienced during its formation. Astronomers now believe that planetary formation in the inner solar system involved dozens of such collisions between planet-sized bodies. The moon-forming impact was simply the last significant one, the final major event in Earth's violent youth. Shortly after its formation, the moon was much closer to Earth than it is today, perhaps only 15,000 to 20,000 miles away, compared to the current average distance of about 238,000 miles. It would have loomed enormous in the sky, appearing many times larger than it does now. The tidal forces between the two bodies would have been immense, raising tremendous tides in the molten rock of both worlds. The young moon was also extremely hot. The energy from accretion, combined with the radioactive decay of elements within its interior, kept the moon molten for millions of years. The entire lunar surface may have been covered in a magma ocean, a global sea of molten rock hundreds of miles deep. As this magma ocean cooled over tens of millions of years, different minerals crystallized at different depths, creating the layered structure we see today. The lighter minerals, particularly a form of calcium-rich feldspar called anorthite, floated to the surface, forming the bright, ancient highlands that cover much of the moon. The denser minerals sank deeper, forming the mantle. This process, called differentiation, gave the moon its fundamental structure: a thick feldspar crust, a mantle of denser silicate rocks, and a small metallic core. The formation of the moon through this giant impact had profound consequences for Earth as well. The collision added angular momentum to the Earth-Moon system, making Earth spin faster. In those early days, an Earth day may have been only 5 or 6 hours long. The impact also tilted Earth's axis, giving our planet the axial tilt of about 23.5 degrees that creates our seasons. Over the billions of years since, the moon has been gradually moving away from Earth, and Earth's rotation has been slowing down, but we will return to that story later. For now, it is enough to know that the moon was born in violence, forged in the fires of a planetary collision, and shaped by the slow cooling of a world-spanning ocean of molten rock. The moon's structure and composition. If you could slice the moon in half and peer inside, you would see a world built in layers, each telling part of the story of its formation and evolution. Unlike Earth, which remains geologically active with its churning mantle and moving tectonic plates, the moon is a quiet, ancient body, frozen in time since its early history. The moon's interior structure consists of 3 main regions: the crust, the mantle, and the core. The crust is the outermost layer, the rocky shell we see from Earth. It averages about 70 kilometers thick, though it varies considerably from place to place. On the near side of the moon, the side that always faces Earth, the crust is thinner, perhaps only 30 to 40 kilometers thick in some areas. On the far side, the crust is much thicker, averaging about 100 kilometers or more in some regions. This asymmetry is one of the moon's enduring mysteries. Why should the crust be thinner on one side than the other? Scientists have several hypotheses. One possibility is that the tidal forces from Earth during the moon's early molten phase influenced how the crust formed and solidified. Another suggestion is that a second, smaller impact on the far side may have thickened the crust there. Whatever the cause, this difference in crustal thickness has had important consequences for the moon's geological history. The lunar crust is composed primarily of anorthosite, a rock type made almost entirely of the mineral anorthite. This is the material that makes up the bright lunar highlands, the lighter-colored regions visible to the naked eye from Earth. Anorthosite formed when the moon's magma ocean cooled and the lighter feldspar minerals floated to the surface, crystallizing into a solid crust. This process took place very early in the moon's history, between 4.1 and 4.4 billion years ago. Radiometric dating of lunar rocks returned by the Apollo missions confirmed this ancient age. Some highland samples are among the oldest rocks ever analyzed, with ages approaching 4.46 billion years. These rocks are older than almost any rock found on Earth, because Earth's active geology, including plate tectonics and erosion, has destroyed or recycled its most ancient surfaces. The moon, being geologically dead, has preserved a record of the early solar system that Earth cannot provide. Beneath the crust lies the lunar mantle, a thick layer of denser silicate rocks extending about 849 miles deep. The mantle is composed primarily of minerals like pyroxene and olivine, which are heavier than the feldspar-rich crust and sank deeper during the moon's early differentiation. Unlike Earth's mantle, which convects and flows slowly over geological time, driving plate tectonics and volcanic activity, the moon's mantle is largely solid and inert. However, the mantle was not always completely solid. For billions of years after the moon formed, portions of the mantle remained hot enough to melt, producing magma that rose toward the surface. This magma erupted through volcanic fissures and flooded the low-lying impact basins, creating the dark plains we call Maria, Latin for seas. These volcanic eruptions continued for at least 1 billion years, with most of the mare basalts forming between 3 and 3.5 billion years ago, though some flows may be as young as 1.2 billion years. The mare basalts are chemically distinct from the highland anorthosites. They are darker, richer in iron and magnesium, and denser. When you look at the moon with the naked eye, the dark patches you see are these ancient lava flows, still visible billions of years after they cooled and solidified. At the very center of the moon lies the core, a small metallic heart composed primarily of iron, with some nickel. The moon's core is tiny compared to Earth's, with a radius of only about 205 miles. The core consists of a solid inner core about 150 miles thick and a fluid outer core about 56 miles thick. This small core size reflects the moon's origin in the giant impact, which stripped away much of the iron-rich material that would otherwise have sunk to form a larger core. We know the moon has a core not by direct observation, but through indirect evidence. Seismometers left on the lunar surface by Apollo astronauts detected moonquakes, and by studying how seismic waves traveled through the moon's interior, scientists were able to map its internal structure. The moon also has a very weak magnetic field today, but measurements of lunar rocks show that some of them were magnetized billions of years ago, suggesting the moon once had a stronger magnetic field, perhaps generated by convection in a molten core. The moon's overall composition is depleted in certain elements compared to Earth. Beyond the lack of iron in the core, the moon is also depleted in volatile elements like potassium, sodium, and zinc. These elements tend to evaporate at relatively low temperatures, and they were lost during the intense heat of the giant impact and the subsequent period when the moon was molten. The moon is essentially a bone-dry world, or at least it was thought to be until recently. We will explore the surprising discovery of water ice in later sections. Another distinctive feature of the moon's composition is the presence of a geochemical signature called CREEP, an acronym for potassium K, rare earth elements REE, and phosphorus P. CREEP is found in some lunar rocks and represents the last bit of liquid magma that crystallized as the magma ocean cooled. This material became enriched in elements that do not easily fit into common minerals, concentrating them in the final residue. CREEP is especially abundant in certain regions of the moon and has no known equivalent on Earth, making it one of the moon's unique chemical fingerprints. The moon's low density, its small core, its bone-dry composition, and its ancient differentiated crust all tell the same story. A world born in violence, shaped by intense heat and frozen in time once its internal energy dissipated. The moon is a time capsule preserving a record of processes that occurred in the first few 100 million years of the solar system's existence. Distance, orbit, and motion. The moon dances with Earth in a gravitational embrace that has persisted for more than 4 billion years. It is a dance that follows precise mathematical laws, yet remains dynamic and ever-changing. To understand the moon's motion is to understand one of the most fundamental relationships in our corner of the solar system. On average, the moon orbits Earth at a distance of about 384,400 kilometers, or roughly 238,900 miles. To put that in perspective, you could fit about 30 Earths side by side in the space between Earth and the moon. It seems like a vast gulf, and it is, but in astronomical terms, the moon is our closest companion by far. However, this distance is not constant. The moon's orbit around Earth is not a perfect circle, but an ellipse, a slightly stretched circle with Earth located at one of the two foci. This means that sometimes the moon is closer to Earth and sometimes it is farther away. When the moon reaches its closest approach, a point called perigee, it comes within about 363,300 kilometers of Earth's center. At its farthest point, called apogee, the moon recedes to about 405,500 kilometers. This variation of more than 42,000 kilometers means that the moon's apparent size in our sky changes noticeably over the course of a month. At perigee, the moon appears about 14% larger in diameter and about 30% brighter than at apogee. When a full moon coincides with perigee, we get what has become popularly known as a supermoon, an event that occurs a few times each year. The moon's proximity makes it look impressively large, though the difference is subtle enough that most casual observers might not notice without side-by-side comparison. The moon completes one orbit around Earth in about 27.3 days. This is called the sidereal month, the time it takes for the moon to return to the same position relative to the background stars. However, because Earth is also orbiting the Sun during this time, the moon needs a bit longer to return to the same phase, such as from one full moon to the next. This longer period, called the synodic month, lasts about 29.5 days. As the moon orbits Earth, it also rotates on its own axis. Remarkably, the moon's rotation period is exactly the same as its orbital period. This phenomenon is called tidal locking or synchronous rotation. It means that the moon keeps the same face turned toward Earth at all times. We always see the same lunar features, the same Maria and craters arranged in the familiar pattern some people call the man in the moon. Tidal locking was not always the case. When the moon first formed, it rotated much faster. But Earth's gravity raised tidal bulges on the moon, just as the moon raises tides on Earth. These bulges created friction as the moon rotated, and this friction acted like a brake, gradually slowing the moon's rotation over millions of years until its spin became synchronized with its orbit. This same process is still happening in reverse. The moon's gravity raises tides in Earth's oceans, and as Earth rotates beneath these tidal bulges, friction transfers energy from Earth's rotation to the moon's orbit. This has two effects. Earth's rotation is gradually slowing down, making our days longer, and the moon is gradually moving away from Earth. The rate of this recession is remarkably precise. Laser ranging experiments, which bounce laser beams off reflectors left on the lunar surface by Apollo astronauts, have measured the moon's retreat at about 3.8 centimeters per year. That is roughly the rate at which your fingernails grow. It seems tiny, but over geological time it adds up. When the moon first formed, it may have been only 15,000 to 20,000 miles from Earth. It would have appeared enormous in the sky, perhaps 10 to 15 times larger than it does today. The tides it raised on the young, molten Earth would have been hundreds of feet high, massive surges of liquid rock rising and falling as the nearby moon passed overhead. Over the next 4.5 billion years, the moon slowly spiraled outward to its current distance. Evidence for this comes from multiple sources: fossilized stromatolites, layered structures created by ancient photosynthetic bacteria, show daily and monthly growth patterns from 850 million years ago. By counting these layers, scientists determined that at that time an Earth day was only about 21 hours long, and there were more days in a year. Fossil corals from 400 million years ago show similar evidence of a 22-hour day. Going back even further to 620 million years ago, tidal rhythmites, sedimentary rocks that record the patterns of ancient tides, show that the moon was receding at an average rate of about 22 millimeters per year, and that Earth days were lengthening by about 12 microseconds per year. These rates are about half of what we measure today, which makes sense given the complex dynamics involved and the changing configuration of Earth's continents and oceans over time. The Moon's elliptical orbit has another consequence. Its orbital speed changes. According to Kepler's laws of planetary motion, an object in an elliptical orbit moves faster when it is closer to the body it orbits and slower when it is farther away. At perigee, the Moon travels at about 1.1 kilometers per second, while at apogee it slows to about 0.96 kilometers per second. The Moon's orbit is also tilted by about 5 degrees relative to Earth's orbit around the Sun, a plane called the ecliptic. This tilt means that the Moon does not always pass directly in front of the Sun during a new moon, or directly through Earth's shadow during a full moon. Most months, the Moon passes above or below these alignment points. But when the Moon's orbit does cross the ecliptic plane at the same time as a new or full moon, we get eclipses. Solar eclipses occur when the Moon passes directly between Earth and the Sun, and lunar eclipses occur when Earth passes directly between the Sun and the Moon. There is another subtle motion to observe. Even though the Moon is tidally locked, we can actually see slightly more than half of its surface over time, about 59% in total. This is due to a phenomenon called libration. Because the Moon's orbit is elliptical and its rotation is constant, there are times when its orbital motion gets slightly ahead of its rotation, allowing us to peek around one edge, and other times when its rotation gets slightly ahead, letting us see around the opposite edge. There is also a slight north-south libration, because the Moon's rotation axis is tilted relative to its orbital plane. The Moon's motion is predictable, governed by the laws of gravity and orbital mechanics worked out centuries ago by Newton and refined by Einstein. Yet even now, with lasers measuring its distance to millimeter precision and computers modeling its orbit with extraordinary accuracy, the Moon continues to hold mysteries. Its recession is not perfectly constant. It seems to have accelerated in recent geological time. The reasons for this are still being investigated, possibly related to changes in Earth's ice sheets, ocean basins, and the distribution of mass on our planet. The Moon is drifting away, slowly but inexorably, carried outward by the same tidal forces that locked its face to ours billions of years ago. In the far future, billions of years from now, the Moon will be much farther than it is today, appearing smaller in our sky, raising gentler tides on our oceans. But for now, it hangs in the night, 238,000 miles away, a constant companion in the darkness. Lunar phases and the lunar cycle. Look up at the Moon on any given night, and you will see it wearing a different face. Sometimes it is a slender crescent, delicate as a fingernail. Sometimes it is half lit, split down the middle between light and shadow. Sometimes it shines full and round, bright enough to cast shadows on Earth. And sometimes during the new moon it disappears entirely from the night sky. These changing appearances are the lunar phases, and they are one of the most familiar yet often misunderstood phenomena in the night sky. The Moon does not change shape. It does not glow with its own light. It is always a sphere, always illuminated on one side by the sun. What changes is our perspective, the angle from which we see the sunlit portion of the Moon as it orbits Earth. The cycle of lunar phases repeats every 29.5 days, a period called a lunation or synodic month. This cycle is divided into 8 distinct phases: new moon, waxing crescent, first quarter, waxing gibbous, full moon, waning gibbous, third quarter, and waning crescent. Let us begin with the new moon. During this phase, the Moon lies between Earth and the Sun. The side of the Moon facing Earth is in shadow. receiving no direct sunlight, while the far side is fully illuminated. We cannot see the new moon in the sky, at least not easily, because the dark side is turned toward us, and because it rises and sets with the sun. A day or two after new moon, the moon has moved slightly in its orbit, and a thin sliver of its sunlit side becomes visible from Earth. This is the waxing crescent phase. The term waxing means growing, and over the next week this crescent thickens as more of the moon's sunlit side comes into view. About 7 days after new moon, the moon reaches first quarter. This name is confusing because the moon appears half lit, not 1/4 lit. The term refers to the moon's position in its orbit. It has completed 1/4 of its journey around Earth. From our perspective, we see exactly half of the moon's near side illuminated, split vertically between light and dark. The illuminated portion continues to grow through the waxing gibbous phase. Gibbous comes from a Latin word meaning hump-backed, describing the moon's bulging, more than half-lit appearance during this phase. 2 weeks after new moon, the moon reaches the full moon phase. Now Earth lies between the moon and the sun. The entire near side of the moon is bathed in sunlight, and we see a complete, bright disk. Full moons rise around sunset and set around sunrise, visible all night long. After full moon, the illuminated portion begins to shrink or wane. The moon enters the waning gibbous phase, still more than half lit but diminishing. Then it reaches third quarter, again appearing half lit but on the opposite side from first quarter. Finally, it becomes a waning crescent, a thinning sliver of light in the pre-dawn sky, until the cycle completes and we arrive at new moon once more. This entire sequence is driven by geometry. As the moon orbits Earth, the angle between the sun, moon and Earth changes continuously. This changes the portion of the sunlit moon visible from Earth. Half of the moon is always illuminated by the sun, just as half of Earth always experiences daylight. But our view of that illuminated half changes as the moon moves. The lunar cycle has fascinated humanity since ancient times. Many cultures based their calendars on the moon, using the easily observable phases to mark the passage of time. The Islamic calendar, for example, is a purely lunar calendar, with each month beginning when the first crescent of a new moon is visible. The Hebrew calendar and traditional Chinese calendar are lunisolar, attempting to reconcile the 29.5-day lunar month with the 365-day solar year through complex systems of leap months. Even today, the lunar cycle influences aspects of our culture, from the timing of religious holidays to the folklore surrounding full moons. The names we give to each month's full moon, such as harvest moon or hunter's moon, come from Native American and early American traditions linking the lunar cycle to seasonal activities. There is a difference between the synodic month of 29.5 days and the sidereal month of 27.3 days mentioned earlier. The synodic month is the time between successive new moons or between successive full moons, the time it takes for the Sun-Earth-Moon geometry to repeat. The sidereal month is the time it takes for the moon to complete one orbit relative to the background stars. Why the difference? Because Earth is also orbiting the sun. During the 27.3 days it takes the moon to complete one orbit around Earth, Earth has moved about 27 degrees along its own orbit around the sun. For the moon to return to the same phase, such as new moon, it needs to travel an extra 27 degrees to catch up to the new Sun-Earth-Moon alignment. This takes about 2 additional days, bringing the total to 29.5 days. The lunar phases also relate to the timing of eclipses. Lunar eclipses can only occur during a full moon, when Earth is positioned between the Sun and Moon. If the Moon's orbit around Earth were in the same plane as Earth's orbit around the Sun, we would get a lunar eclipse every full moon. But because the Moon's orbit is tilted by about 5 degrees, most full moons pass above or below Earth's shadow. Only when a full moon occurs near one of the 2 points where the Moon's orbit crosses the ecliptic plane, called nodes, does the Moon pass through Earth's shadow and we witness a lunar eclipse. Similarly, solar eclipses can only occur during a new moon, when the Moon passes between Earth and the Sun. Again, because of the 5-degree tilt, most new moons pass above or below the Sun as seen from Earth. Only when a new moon occurs near a node does the Moon's shadow fall on Earth, creating a solar eclipse. During a waxing or waning crescent phase, you may notice a faint glow illuminating the dark portion of the Moon. This is called Earthshine, and it is sunlight that is reflected off Earth, then bounced off the Moon's surface back to our eyes. Earth, with its clouds and oceans, reflects quite a bit of sunlight, enough to dimly light up the Moon's shadowed side. The effect is sometimes called the old moon in the new moon's arms, or the new moon in the old moon's arms, depending on whether the crescent is waxing or waning. The Moon's phases are a simple consequence of light and geometry, yet they have profound beauty and complexity when observed carefully over time. The Moon waxes and wanes, appears and disappears, but always returns, reliable and unchanging in its cycle. It is a clock in the sky, marking time not in hours but in the slow turning of orbits and the interplay of sunlight and shadow. The Moon's surface, craters and maria. If you look at the Moon through even a small telescope, the first thing that strikes you is the sheer number of craters. They cover the surface in overlapping profusion, large and small, fresh and ancient, a record of billions of years of cosmic bombardment. The Moon's craters are almost entirely the result of impacts, collisions with asteroids, comets, and meteoroids that have rained down from space since the Moon formed. Unlike Earth, which has an atmosphere to burn up small incoming objects and geological processes that erase or bury old craters, the Moon has neither. Its surface is ancient and unchanging, preserving a near-complete record of impacts stretching back more than 4 billion years. When an object from space strikes the Moon, it is typically traveling faster than the speed of sound, often tens of kilometers per second. The kinetic energy of such a collision is immense. Upon impact, the asteroid or meteoroid is instantly vaporized, and a shock wave propagates through the lunar crust. Rock is melted, shattered, and thrown outward in an explosion of debris. This process creates a crater in 2 main phases, excavation and modification. During excavation, material is blasted out of the ground, forming a bowl-shaped cavity. The debris, called ejecta, is thrown outward in a curtain of rock and dust that falls back to the surface around the crater, creating rays and blankets of lighter-colored material. During the modification phase, the crater's shape changes. The walls may slump inward due to gravity. If the crater is large enough, the center may rebound, forming a central peak as the compressed rock beneath the impact site springs back. Very large craters, those more than 300 kilometers across, are called impact basins and may have multiple concentric rings created by the enormous forces involved. The largest crater on the Moon, and indeed one of the largest known impact structures in the solar system, is the South Pole Aitken Basin on the far side. This colossal scar is about 2,500 kilometers in diameter and more than 8 kilometers deep. It formed very early in the Moon's history, perhaps as much as 4.3 billion years ago, when an asteroid the size of a small planet smashed into the lunar far side with devastating force. The moon's cratered highlands are the oldest parts of the lunar surface, dating back to the very early days of the solar system, between about 4.1 and 3.8 billion years ago. The moon, along with Earth and the other inner planets, experienced a period of intense bombardment. This event is called the Late Heavy Bombardment, and it was likely caused by a reorganization of the orbits of the giant planets, particularly Jupiter and Saturn, which scattered icy bodies from the outer solar system inward toward the Sun. During this period, massive impacts carved out the large basins that dominate the near side of the moon. Mare Imbrium, the largest of the dark maria visible to the naked eye, is an impact basin about 145 kilometers in diameter. It formed around 3.9 billion years ago when an asteroid, perhaps 250 kilometers across, struck the moon with unimaginable force. The impact excavated the basin and created mountain ranges around its rim, including the Lunar Alps and Apennines, some of which rise several kilometers above the surrounding terrain. But the basins we see today are not simply empty bowls of rock. They are filled with dark, smooth material that gives them their distinctive appearance. These dark plains are the lunar maria, Latin for seas, named by early astronomers who thought they might be bodies of water. They are nothing of the sort. The maria are vast floods of basaltic lava, volcanic rock that erupted from the moon's interior and flowed into the low-lying impact basins. The lava came from deep within the moon's mantle, where radioactive decay and residual heat from the moon's formation kept rock molten for billions of years. When impacts cracked through the crust, especially in places where the crust was thin, this magma found pathways to the surface. The Mare eruptions did not happen immediately after the basin-forming impacts. There is typically a gap of 100 million years or more between the time a basin formed and when lava began to fill it. Most Mare volcanism occurred between 3.8 and 3.2 billion years ago, though some flows continued until as recently as 1.2 billion years ago. Samples returned by China's Chang'e 5 mission in 2020 showed basalts as young as 2 billion years, indicating that volcanic activity on the moon persisted longer than previously thought. The Mare basalts are darker than the highland and orthosites because they are richer in iron and other heavy elements. They are also smoother because the lava flows buried the older craters that existed before the eruptions. If you look at the moon, you will notice that the maria have far fewer craters than the highlands, simply because they are younger surfaces that have had less time to accumulate impacts. The distribution of maria across the moon is not uniform. The near side of the moon has much more Mare material than the far side. About 31% of the near side is covered by maria, while only 2% of the far side is. This asymmetry is related to the difference in crustal thickness. The near side crust is thinner, making it easier for magma to reach the surface. The far side crust is much thicker, and most of the far side basins were never flooded with lava. Why the crust is thinner on the near side remains one of the moon's great unsolved mysteries. It may be related to tidal heating from Earth during the moon's early history, or to the redistribution of heat-producing radioactive elements, or to some other process we do not yet fully understand. Some of the moon's most prominent craters are relatively young and have distinctive features. Tycho, located in the southern highlands, is only about 108 million years old, a mere blink of an eye in lunar time. It is about 85 kilometers in diameter and is famous for its bright ray system, long streaks of ejected material that radiate across the lunar surface for hundreds of kilometers. These rays are visible even to the naked eye during a full moon, appearing as bright lines emanating from the crater. Copernicus, another relatively young crater at about 800 million years old, is about 93 kilometers across and features a prominent central peak and terraced walls. It lies at the southern edge of Mare Imbrium and is one of the most studied craters on the Moon. Clavius, one of the largest craters visible from Earth, is about 225 kilometers in diameter. It is ancient and heavily cratered itself, with smaller impacts having occurred within its walls over billions of years, creating a layered record of the bombardment history. The Moon's surface is also marked by other volcanic features besides the Maria. Sinuous rills are winding channels that look like dried-up riverbeds. They were likely formed by flowing lava, either as lava channels or as collapsed lava tubes where molten rock once flowed beneath a solidified crust. Some rills are hundreds of kilometers long and several kilometers wide. There are also features called wrinkle ridges, low linear hills that snake across the Maria. These are thought to be compressional features formed as the lava cooled and contracted, or as the underlying crust adjusted to the weight of the lava. The Moon's surface has no erosion in the traditional sense. There is no wind, no rain, no flowing water, but the surface is not entirely static. Over billions of years, the constant rain of micrometeorites, cosmic rays, and charged particles from the Sun gradually breaks down the surface rock, creating a layer of fine dust and rock fragments called regolith. This regolith covers the entire lunar surface to a depth of several meters in most places, and it is why the Moon appears grey and dusty in photographs taken by astronauts. The regolith is a mixture of rock fragments, mineral grains, bits of glass formed by the heat of impacts, and tiny spheres of once molten material. It is fine like talc powder in some places and coarse like sand in others. The Apollo astronauts found it sticky and abrasive, clinging to their spacesuits and equipment. The Moon's craters and Maria are not just geological features. They are history written in stone, a record of 4.5 billion years of impacts, volcanism, and cosmic bombardment. They tell us about the early solar system, about the rain of debris that fell on all the inner planets, and about the internal evolution of a world that cooled and died billions of years ago. Every crater is a moment frozen in time, every lava flow a glimpse into the Moon's molten heart. Tides and gravitational dance. Twice each day the oceans rise and fall, waves crash higher on the beach then retreat, exposing sand and rock that moments before were underwater. This rhythm, as old as the oceans themselves, is the work of the Moon. Tides are one of the most visible consequences of the Moon's gravitational pull on Earth. Understanding them requires understanding not just gravity, but the way gravity varies with distance and how it interacts with Earth's rotation. Gravity is a force that pulls masses toward each other, and the strength of that pull decreases with distance. The Moon's gravity tugs on everything on Earth, but it tugs harder on the parts of Earth that are closer to it, and less hard on the parts that are farther away. This difference in gravitational pull across Earth's diameter is called a gravitational gradient or tidal force. Imagine Earth as it truly is, a mostly solid sphere covered with oceans. The side of Earth facing the Moon experiences slightly stronger gravitational pull than Earth's center, and Earth's center experiences slightly stronger pull than the far side. This differential force stretches Earth very slightly into the shape of an elongated ellipsoid, like a football, with bulges on both the near and far sides. For the solid body of Earth, this deformation is small, only a few centimeters, but the oceans, being fluid, respond much more dramatically. The water on the side facing the Moon is pulled toward the Moon, creating a bulge of high tide. On the opposite side of Earth, the water is left behind, creating another bulge of high tide. Between these two bulges, at the places 90 degrees away from the moon, the water level drops, creating low tides. As Earth rotates on its axis, different parts of the planet pass through these tidal bulges. Most coastal locations experience 2 high tides and 2 low tides each day, roughly 12 hours apart, as they rotate through the near side bulge, then the far side bulge, and through the 2 low tide regions in between. The sun also creates tides on Earth, but the moon's tides are much stronger. This seems counterintuitive at first, because the sun is vastly more massive than the moon and exerts a much stronger overall gravitational pull on Earth. But tides are not caused by the overall strength of gravity. They are caused by the difference in gravity from one side of Earth to the other, the gravitational gradient. Because the sun is so far away, about 400 times farther than the moon, its gravitational pull varies much less from one side of Earth to the other. The moon, being much closer, creates a steeper gradient. As a result, the moon's tidal force is more than twice as strong as the sun's. However, the sun's contribution is not negligible. When the sun, moon, and Earth align during a new moon or full moon, the sun's tidal force adds to the moon's, creating especially high tides called spring tides. The name has nothing to do with the season. It comes from the idea that the tides spring forth or leap higher than usual. During spring tides, high tides are higher than average, and low tides are lower than average. When the sun and moon are at right angles to each other, during the first and third quarter moons, their tidal forces partially cancel out, creating neap tides. During neap tides, the difference between high and low tide is smaller than average. The word neap comes from an Old English term meaning without the power, reflecting the reduced tidal range. The timing and height of tides are also influenced by the moon's distance from Earth. When the moon is at perigee, its closest approach, its gravitational pull is stronger and the tidal range is increased. If perigee coincides with a new or full moon, creating what is sometimes called a perigean spring tide or king tide, the tidal range can be especially dramatic. Conversely, when the moon is at apogee, the tides are weaker. The shape of coastlines, the depth of the ocean, and the presence of narrow channels and bays can dramatically amplify tidal effects. The Bay of Fundy in eastern Canada has the highest tidal range in the world, with water levels rising and falling by as much as 16.3 meters, or more than 50 feet, between low and high tide. This extreme range is caused by the funnel shape of the bay, which concentrates and amplifies the tidal bulge as it flows into the narrowing channel. In contrast, tides in the open ocean are much smaller, typically less than a meter. Lakes and enclosed seas also experience tides, but the tidal range is so small, often just a few centimeters, that it is difficult to notice. The moon's gravitational pull does not just raise tides in water, it also raises tides in the solid Earth itself. The entire planet deforms slightly under the moon's influence, rising and falling by about 30 centimeters twice a day. These solid Earth tides are detectable with sensitive instruments, but are not noticeable in everyday experience. The Earth's gravity also raises tides on the moon. Because the moon is smaller and has no oceans, these tides affect the solid body of the moon, causing it to bulge toward and away from Earth. Measurements using laser ranging have shown that the moon's surface rises and falls by about 10 to 15 centimeters due to Earth's tidal forces. These lunar tides create stresses within the moon, and some scientists believe they may be responsible for shallow moonquakes that occur when the moon is closest to Earth. The most important long-term consequence of tides is the exchange of energy and angular momentum between Earth and the moon. As Earth rotates beneath the tidal bulges raised by the moon, Friction from the moving water creates a drag on Earth's rotation. This friction gradually slows Earth's rotation, making days longer. At the same time, the energy lost by Earth's rotation is transferred to the Moon's orbit, causing the Moon to spiral slowly outward. This process has been happening for billions of years. When the Moon first formed, it was much closer to Earth, and Earth was spinning much faster. An Earth day may have been only 5 or 6 hours long. Over time, tides have braked Earth's rotation and pushed the Moon away, creating the configuration we see today. Fossil evidence confirms this. Ancient corals and other organisms that grew in daily and seasonal rhythms have left records in their growth patterns. By counting growth rings in 400-million-year-old fossil corals, scientists determined that a year at that time contained about 400 days, meaning each day was only about 22 hours long. Going back further to 850 million years ago, fossil stromatolites suggest days were about 21 hours long. The process continues today. Each century, Earth's day lengthens by about 2.4 milliseconds. That is an imperceptibly small amount, but over millions and billions of years it adds up. In the far future, if nothing interrupts the process, Earth and the Moon will eventually become tidally locked to each other, just as the Moon is already tidally locked to Earth. At that point, Earth's rotation period and the Moon's orbital period will be the same, both lasting about 47 Earth days. The Moon will hang motionless in the sky above one hemisphere of Earth, never rising or setting, while the other hemisphere will never see it at all. However, this state will never be reached. The process would take about 50 billion years, far longer than the remaining lifetime of the Sun, which will become a red giant and possibly engulf both Earth and Moon in about 5 billion years. Tides are a beautiful example of the interconnectedness of celestial mechanics. The Moon's gravity pulls on the ocean's motion slows Earth's rotation, Earth's slowing rotation pushes the Moon away, and the Moon's recession weakens the tides, creating a feedback loop that has shaped the Earth-Moon system for billions of years. The tides are not just a curiosity or an inconvenience for sailors and beachgoers. They have profound effects on Earth's climate and biology. Tidal currents mix and oxygenate ocean water, supporting marine ecosystems. The intertidal zone, the area between high and low tide, is one of the most biologically productive and diverse habitats on Earth. Tides also help distribute heat and nutrients in the oceans, influencing weather patterns and ocean circulation. Some scientists believe that tides may have played a crucial role in the origin of life. The rhythmic wetting and drying of intertidal zones could have concentrated organic molecules and driven the chemical reactions necessary for life to emerge. The Moon, in this view, is not just a passive companion, but an active participant in making Earth a habitable world. The Moon pulls on Earth, Earth pulls on the Moon, and together they dance a slow waltz through space, bound by gravity, shaped by time. The Apollo missions, on July 20th, 1969, a human being stood on another world for the first time in history. Neil Armstrong descended the ladder of the Lunar module Eagle, stepped onto the powdery surface of the Moon, and spoke words that would echo through time. That's one small step for man, one giant leap for mankind. The Apollo program, which carried 12 astronauts to the lunar surface between 1969 and 1972, was one of the greatest technological and exploratory achievements in human history. It was born from Cold War competition driven by President John F. Kennedy's challenge in 1961 to land a man on the Moon and return him safely to Earth before the decade was out. It required the efforts of more than 400,000 people, cost $25 billion in 1960s currency, and pushed the limits of engineering, science, and human courage. The road to the moon was not easy. The program suffered a tragic setback in 1967 when a fire during a ground test killed 3 astronauts, Virgil Grissom, Edward White, and Roger Chaffee. The fire, which occurred in the command module during what was supposed to be a routine test, led to a complete redesign of the spacecraft and a renewed focus on safety. But the program recovered. Apollo 7, launched in October 1968, was the first crewed mission, testing the redesigned command module in Earth orbit for 11 days. Apollo 8 followed in December 1968, carrying 3 astronauts, Frank Borman, James Lovell, and William Anders, on the first crewed journey to the moon. They did not land, but they orbited the moon 10 times, becoming the first humans to see the far side with their own eyes and the first to witness Earthrise, our blue planet rising above the grey lunar horizon. Apollo 9 tested the lunar module in Earth orbit. Apollo 10 was the full dress rehearsal, flying the lunar module to within 15 kilometers of the moon's surface before returning to the command module, testing every aspect of the landing mission except the actual touchdown. And then came Apollo 11. On July 16, 1969, a Saturn V rocket, the most powerful machine ever built, lifted off from Cape Kennedy carrying Neil Armstrong, Edwin Buzz Aldrin, and Michael Collins. 4 days later, Armstrong and Aldrin descended to the surface in the lunar module Eagle, while Collins remained in orbit aboard the command module Columbia. The descent was not entirely smooth. The lunar module's guidance computer triggered alarms as it ran out of memory during the descent, but mission controllers determined it was safe to continue. Then, as the module neared the surface, Armstrong saw that the planned landing site was covered with boulders. He took manual control and flew the module past the rocks, searching for a clear spot. With fuel running low, he brought Eagle down in the Sea of Tranquility, with only seconds of fuel remaining. 6 hours later, after checking their equipment and preparing their spacesuits, Armstrong opened the hatch and stepped out onto the lunar surface. Aldrin followed 20 minutes later. Together, they spent about 2.5 hours outside the lunar module, setting up scientific experiments, collecting rock samples and planting an American flag. They spoke by phone with President Richard Nixon, left a plaque commemorating the landing, and took photographs that would become iconic images of human exploration. The rocks they collected, 21.5 kilograms of lunar material, were the first samples ever returned from another world. When scientists analyzed them, they found rocks unlike any on Earth, some more than 4 billion years old, bone dry and rich in information about the moon's history and the early solar system. Apollo 12, launched in November 1969, made a precision landing near the Surveyor 3 probe, which had landed on the moon 2 years earlier. Astronauts Pete Conrad and Alan Bean spent over 7 hours on the surface, collected more samples, and even retrieved parts of the Surveyor probe to study how it had weathered exposure to the lunar environment. Apollo 13, launched in April 1970, was intended to land in the Fra Mauro Highlands, but an oxygen tank exploded 2 days into the mission, crippling the command module and forcing the crew to abandon the landing. In one of the most dramatic rescues in the history of spaceflight, astronauts James Lovell, Jack Swigert, and Fred Hayes used the lunar module as a lifeboat, looping around the moon and returning safely to Earth. The mission was a failure as a lunar landing, but a triumph of problem-solving and teamwork. Apollo 14, in February 1971, finally reached Fra Mauro. Astronauts Alan Shepard and Edgar Mitchell spent over 9 hours on the surface, collecting samples and conducting experiments. Shepard famously hit a golf ball on the moon, driving it, as he said, miles and miles and miles in the low gravity. Apollo 15 in July 1971 was the first of the extended J-type missions, equipped with a lunar roving vehicle, essentially a battery-powered car that allowed astronauts to travel much farther from the landing site. David Scott and James Irwin spent nearly 19 hours on the surface over 3 days, driving more than 27 kilometers and collecting 77 kilograms of samples. Among their finds was the Genesis Rock, a piece of ancient anorthosite estimated to be 4.46 billion years old, one of the oldest rocks ever found. Apollo 16, in April 1972, landed in the Descartes Highlands, and Apollo 17, in December 1972, was the final mission. Apollo 17 carried geologist Harrison Schmitt, the only professional scientist to walk on the moon. Schmitt and Eugene Cernan spent over 22 hours on the surface, collecting 243 pounds of lunar samples, the largest haul of any Apollo mission. One of the most important discoveries of Apollo 17 was orange soil, volcanic glass formed during an ancient eruption. This provided direct evidence that the moon had once been volcanically active. Cernan and Schmitt also explored the Taurus Littrow Valley, a deep canyon filled with ancient rocks and surrounded by towering mountains. When Cernan climbed back into the lunar module for the last time, he spoke words that marked the end of an era. As we leave the moon at Taurus Littrow, we leave as we came, and God willing, as we shall return, with peace and hope for all mankind. As of today, no human has returned to the moon since December 1972. In total, the 6 successful Apollo landings returned 842 pounds, or 382 kilograms of lunar rocks and soil to Earth. These samples have been studied continuously for more than 50 years and continue to yield new insights. They revealed that the moon is ancient, geologically dead, bone dry in most places, and chemically similar to Earth in many ways, supporting the giant impact hypothesis. The Apollo missions also left behind scientific instruments. Seismometers recorded moonquakes, providing data about the moon's interior structure. Laser-ranging retroreflectors, mirrors that reflect laser beams sent from Earth, allow scientists to measure the moon's distance with millimeter precision. These instruments are still in use today. The legacy of Apollo extends far beyond the scientific discoveries. It demonstrated what humanity could achieve when driven by a common goal. It inspired generations of scientists, engineers, and explorers. It gave us the first images of Earth as a whole, a fragile blue marble suspended in the darkness, profoundly changing how we see our place in the universe. The Apollo program ended for political and economic reasons, not technical ones. The United States had achieved its goal of landing on the moon before the Soviet Union. Public interest waned as the missions became routine. Budget pressures led to the cancellation of Apollos 18, 19, and 20, and the remaining Saturn V rockets were used for other purposes, including launching the Skylab space station. But the dream did not die. Plans are now underway for new missions to the moon. NASA's Artemis program aims to return astronauts to the lunar surface, including the first woman and the first person of color to walk on the moon. These missions will land near the lunar South Pole, where water ice may exist in permanently shadowed craters, and will lay the groundwork for a sustained human presence on the moon. The Apollo missions were not just about planting flags and collecting rocks. They were about reaching beyond our world, about testing the limits of what is possible, about looking back at Earth from 250,000 miles away and seeing it as a single, unified, fragile home. The moon became not just a destination, but a mirror reflecting our own humanity. The moon's influence on Earth. The moon is more than a light in the night sky. It is a stabilizing force, a timekeeper, and a sculptor of Earth's environment. Without the moon, Earth would be a profoundly different world, perhaps even uninhabitable. One of the moon's most important contributions to Earth is its stabilizing effect on Earth's axial tilt. Earth's axis is currently tilted at about 23.5 degrees relative to the plane of its orbit around the Sun. This tilt is responsible for the seasons. As Earth orbits the Sun, first the northern hemisphere and then the southern hemisphere tilts toward the Sun, creating summer and winter. This tilt is not fixed in place by any internal mechanism. It is stabilized by the moon's gravitational pull. Computer simulations show that without the moon, Earth's axial tilt would vary chaotically over millions of years, swinging from nearly 0 degrees to as much as 85 degrees. Such dramatic changes would have catastrophic consequences for Earth's climate. If the tilt dropped close to 0, there would be almost no seasons. The equator would remain hot year-round, and the poles would be locked in perpetual cold, with no summer to melt the ice. Conversely, if the tilt increased to 85 degrees, the poles would point almost directly at the Sun during summer, baking in continuous sunlight, while winters would plunge them into total darkness and extreme cold. The resulting climate swings would make it nearly impossible for complex life to adapt and evolve. Mars provides a cautionary example. Mars has 2 small moons, Phobos and Deimos, but they are too small to stabilize the planet's axial tilt. As a result, Mars's tilt has varied wildly over its history, from as little as 10 degrees to more than 60 degrees. This may have contributed to the loss of Mars's atmosphere and water, and to the cold, barren desert it is today. Earth's stable axial tilt, maintained by the moon, has allowed for relatively stable climates over billions of years, giving life the predictable conditions it needs to flourish. The moon's stabilizing presence is one of the reasons Earth has remained habitable for so long. The moon has also played a crucial role in shaping the length of Earth's day. As discussed earlier, tidal friction has gradually slowed Earth's rotation over billions of years. Early in Earth's history, a day may have been only 5 or 6 hours long. The rapid rotation would have created fierce winds and turbulent weather, making the surface a harsh environment. As the moon's tides slowed Earth's rotation, days lengthened, and the environment became gentler. Fossil evidence shows this progression. Ancient stromatolites and tidal rhythmites record the length of days hundreds of millions of years ago. Corals from the Devonian period about 400 million years ago show that a year then contained about 400 days of 22 hours each. Going back further to the Precambrian, about 900 million years ago, days were only about 18 hours long. This gradual lengthening of the day has had profound effects on Earth's climate and life. Longer days mean more time for the sun to heat the surface during the day and more time for cooling at night, moderating temperature extremes. The changing day length has also influenced the evolution of biological rhythms, the circadian clocks that govern the daily cycles of life. The moon's gravitational pull also affects Earth's shape. The solid Earth is slightly deformed by the moon's tidal forces, creating a bulge of about 30 centimeters that moves around the planet as the moon orbits. This may seem small, but it has measurable effects. The constant flexing of Earth's crust from these tides may contribute to geological activity, including earthquakes and volcanic eruptions, though the effect is small compared to the forces generated by plate tectonics. There is even evidence that the moon's tidal forces influence Earth's magnetic field. The motion of conducting fluids, particularly in the molten outer core, generates Earth's magnetic field through a process called the geodynamo. Some studies suggest that tidal forces from the moon and sun may modulate the flow patterns in the core, causing small variations in the strength and orientation of the magnetic field. Beyond these physical effects, the moon has had a profound cultural and psychological influence on humanity. For as long as humans have looked up at the night sky, the moon has been a source of wonder, mystery, and inspiration. It has shaped our calendars, our myths, our art, and our science. Ancient civilizations tracked the moon's phases to measure time. The word month comes from moon, reflecting the lunar cycle of 29.5 days. Many religious and cultural festivals are tied to the lunar calendar. The Islamic calendar is purely lunar, marking the beginning of each month with the first sighting of the new crescent moon. The Hebrew calendar and traditional Chinese calendar are lunisolar, using a complex system of leap months to reconcile the lunar cycle with the solar year. The moon has also been blamed, sometimes fancifully, for influencing human behavior. The word lunacy comes from the Latin word for moon, luna, reflecting an ancient belief that the full moon could cause madness. While modern science has found little evidence that the moon affects human psychology in any direct way, the belief persists in popular culture. What is undeniable is the moon's aesthetic and emotional power. A full moon rising over the horizon, bright and round, has stopped people in their tracks for millennia. Poets have written about it, artists have painted it, and lovers have gazed at it together. The moon is a shared human experience, visible to everyone, everywhere on Earth, a common thread connecting all of us. The moon has also driven human curiosity and ambition. The desire to understand the moon led to the development of telescopes, the study of orbital mechanics, and eventually the space age itself. The Apollo program was in many ways the culmination of thousands of years of looking up and wondering what it would be like to stand on that distant silver world. In all these ways, the moon has shaped Earth and shaped humanity. It is not just a satellite, it is a companion, a guardian, and a muse. Temperature and environment, the moon is a world of extremes. With no atmosphere to trap heat or moderate temperature, the lunar surface experiences some of the most dramatic temperature swings in the solar system. During the lunar day, which lasts about 14 Earth days, the surface bakes under unfiltered sunlight. Temperatures at the equator can reach about 260 degrees Fahrenheit, or 127 degrees Celsius. That is hotter than boiling water, hot enough to melt lead. But when the sun sets and the long lunar night begins, the temperature plummets. With no atmosphere to retain heat, the surface radiates its warmth into space. Nighttime temperatures can drop to about minus 280 degrees Fahrenheit, or minus 173 degrees Celsius. That is colder than the coldest temperature ever recorded on Earth, colder than dry ice, cold enough to freeze almost any substance solid. This range of more than 500 degrees Fahrenheit between day and night is a consequence of the moon's lack of atmosphere. On Earth, our atmosphere acts like a blanket, absorbing heat during the day and releasing it slowly at night, moderating the temperature extremes. The moon has no such protection. The moon does have an extremely thin exosphere, a tenuous cloud of atoms and molecules surrounding it, but it is so insubstantial that it barely counts as an atmosphere at all. The exosphere is about 1 trillion times less dense than Earth's atmosphere at sea level. If you stood on the moon, you would experience it as a perfect vacuum. This exosphere is composed mainly of helium, neon and argon, with trace amounts of sodium, potassium and other elements. These atoms are constantly being replenished and lost. Solar wind particles strike the lunar surface, kicking up atoms that briefly hover above the surface before being either lost to space or reabsorbed by the ground. This process is called sputtering. Some atoms come from the solar wind itself. Helium atoms from the sun are embedded in the lunar soil and slowly released back into the exosphere. Other atoms are released by the decay of radioactive elements in the lunar rocks or by impacts from micrometeoroids. One interesting feature of the moon's exosphere is the sodium tail. When sunlight strikes sodium atoms in the exosphere, it causes them to glow, creating a faint tail that streams away from the moon in the direction opposite the sun, much like a comet's tail. This sodium tail can actually be seen from Earth using specialized telescopes. The absence of an atmosphere has several important consequences. First, there is no wind, no weather, and no erosion by flowing water or air. The only forces shaping the lunar surface are impacts, and the slow breakdown of rocks by micrometeorites and radiation, a process called space weathering. Second, there is no sound. Sound waves require a medium like air or water to travel through, and the moon's vacuum is silent. Astronauts on the moon communicated via radio, and their footsteps, though they kicked up dust, made no sound. Third, the sky on the moon is always black, even during the day. On Earth, our atmosphere scatters sunlight, creating a blue sky. On the moon, there is no scattering, so the sky remains dark and the stars are visible even when the sun is shining. The lack of atmosphere also means that sunlight on the moon is harsh and unfiltered. Ultraviolet radiation, which is absorbed by Earth's ozone layer, reaches the lunar surface at full strength, along with other forms of radiation and high-energy particles from the solar wind and cosmic rays. This radiation environment is hazardous to both humans and equipment. Astronauts on the moon had to be protected by their spacesuits, and long-term exposure could cause serious health problems. Despite the extreme temperatures at the equator, there are places on the moon where the temperature is far more stable. At the lunar poles, the sun never rises very high above the horizon. In fact, because the moon's axis is nearly perpendicular to the plane of the ecliptic, tilted by only about 1.5 degrees, the sun always skims along the horizon at the poles. This means that deep craters at the poles can be in permanent shadow, never receiving any direct sunlight. These permanently shadowed regions are some of the coldest places in the solar system. Temperatures in these shadowed craters can drop to about -400 degrees Fahrenheit, or -240 degrees Celsius. This is cold enough to trap water ice for billions of years. And indeed, water ice has been found in these shadowed craters. For many years, scientists believed the moon was completely dry. The Apollo samples showed no trace of water. The intense heat of the giant impact would have vaporized any water, and the moon's weak gravity and lack of atmosphere would have allowed it to escape into space. But in 2008, the Indian mission Chandrayaan-1 detected the signature of water molecules on the lunar surface. Later missions, including NASA's Lunar Reconnaissance Orbiter and the L-Cross Impact Experiment, confirmed that water ice exists in significant quantities in the permanently shadowed craters at the poles. This discovery has profound implications. Water is essential for human life, and if future lunar bases can access this ice, it could provide drinking water, oxygen for breathing, and even hydrogen and oxygen for rocket fuel. The presence of water makes the moon a more hospitable destination for future exploration and settlement. In addition to water, the shadowed craters may contain other volatile substances that have been cold-trapped over billions of years, including carbon dioxide, methane, and ammonia. Studying these deposits could provide insights into the delivery of volatiles to the inner solar system and the early history of the Moon and Earth. The temperature extremes and vacuum environment of the Moon pose significant challenges for future exploration. Equipment must be designed to withstand both scorching heat and freezing cold, often within the span of a few hours as the sun rises or sets. Electronics can fail, lubricants can freeze or evaporate, and materials can expand and contract, cracking and breaking under the thermal stress. But these challenges are not insurmountable. The Apollo astronauts proved that humans can work on the Moon, and future missions will build on their experience, using better technology and better understanding of the lunar environment. The Moon is harsh, but it is also accessible, lying just 3 days away by spacecraft, a proving ground for the technologies and strategies needed to explore more distant worlds. Far side versus near side. The Moon keeps one face turned toward Earth at all times. This is the near side, the familiar face we see in the night sky, marked by dark Maria and bright highlands. The far side, the hemisphere we cannot see from Earth, remained a mystery until the space age. The terms near side and far side are often confused with light side and dark side, but these are not the same. The far side of the Moon receives just as much sunlight as the near side. There is no permanently dark side. During a new moon, the far side is fully illuminated, while the near side is in shadow. During a full moon, the reverse is true. Over the course of a month, every part of the Moon experiences about 2 weeks of daylight and 2 weeks of night. The reason we see only one side of the Moon is tidal locking, the same process that has locked the Moon's rotation to its orbit. When the Moon first formed, it rotated much faster, but Earth's gravity raised tidal bulges on the Moon's surface. As the Moon rotated, these bulges created friction and drag, gradually slowing the Moon's rotation until its spin rate matched its orbital period. At that point, the same face always pointed toward Earth, and the tidal bulges settled into a stable configuration. Humans got their first glimpse of the far side on October 7, 1959, when the Soviet spacecraft Lunar 3 flew around the Moon and transmitted grainy black and white photographs back to Earth. The images were a revelation. The far side looked different from the near side, with far fewer dark Maria and more heavily cratered highlands. This asymmetry between the near and far sides is one of the Moon's great mysteries. About 31% of the near side is covered by Maria, the dark, basaltic plains formed by ancient lava flows. On the far side, only about 2% is covered by Maria. The far side is dominated by ancient, heavily cratered highlands. Why the difference? The answer lies in the thickness of the lunar crust. The near side crust is thinner, averaging about 30 to 40 kilometers in some regions, while the far side crust is much thicker, averaging about 100 kilometers or more. This difference in crustal thickness made it easier for magma to reach the surface on the near side, and much harder on the far side. When giant impacts created basins on the Moon, they cracked through the crust, creating pathways for magma from the mantle to rise. On the near side, where the crust was thin, this magma could reach the surface relatively easily, flooding the basins with lava. On the far side, the thick crust acted as a barrier, preventing most magma from reaching the surface. Why the crust is thicker on the far side is another mystery. One hypothesis is that the difference is related to the Moon's early thermal history. When the Moon was still molten, tidal heating from Earth may have kept the near side slightly hotter, causing the crust to form thinner on that side. Another idea is that the far side received more impacts very early in the Moon's history, thickening the crust through the addition of ejected material. A recent hypothesis suggests that a collision with a second smaller moon early in the moon's history may have added a thick layer of crust to one side, creating the asymmetry. This second moon, if it existed, would have been created in the same giant impact that formed the main moon, and would have been unstable, eventually colliding with the moon at low speed. Whatever the cause, the asymmetry is real and has been confirmed by multiple missions. NASA's Gravity Recovery and Interior Laboratory GRAIL mission, which flew 2 spacecraft in tandem around the moon to map its gravity field, provided detailed measurements of the crustal thickness and confirmed that the far side crust is indeed much thicker. The far side also has one of the largest and oldest impact features in the solar system, the South Pole Aitken Basin. This enormous scar, about 2,500 kilometers in diameter and more than 8 kilometers deep, was created by a massive impact early in the moon's history. It is so large that it affects the moon's shape and gravity field. Despite its size, the basin was never completely flooded with lava, likely because the far side crust was too thick for magma to reach the surface in large quantities. Although we see the same face of the moon at all times, we can actually see slightly more than half of the lunar surface from Earth over time, about 59% in total. This is due to libration, a subtle rocking motion caused by the moon's elliptical orbit and tilted rotation axis. As the moon speeds up and slows down in its orbit, and as we view it from slightly different angles, the edges of the far side occasionally come into view. The far side of the moon is sometimes called the dark side, but this is a misnomer. The far side receives just as much sunlight as the near side. The term dark in this context means unknown or mysterious, not literally dark. It was the hidden side, the side we could not see until spacecraft ventured around the moon. The far side has a stark, alien beauty. It is more rugged, more heavily cratered, and more ancient-looking than the near side. Without the smooth Maria to break up the landscape, it is a chaotic jumble of overlapping craters, a testament to billions of years of bombardment. For future lunar explorers, the far side offers unique opportunities. It is shielded from Earth's radio noise, making it an ideal location for radio. Telescopes that could observe the universe at wavelengths impossible to detect from Earth. A radio observatory on the far side could peer into the cosmic dark ages, the period before the first stars formed, listening for the faint signals from the early universe. The far side is also of interest for scientific study. Its ancient crust may hold clues to the moon's early history and the processes that shaped it. Missions to the far side are more challenging because they require relay satellites to communicate with Earth, but several missions have already landed there, including China's Chang'e 4 mission, the first soft landing on the lunar far side in January 2019. The near side and far side are 2 halves of the same world, yet they are strikingly different, shaped by the same processes but yielding different outcomes. The moon's 2 faces remind us that every world has its secrets, and exploration is the only way to uncover them. Moonquakes and geological activity. The moon may seem dead and unchanging, but beneath its dusty surface, subtle forces are still at work. The moon experiences moonquakes, seismic tremors that shake the lunar interior, and its surface continues to evolve, albeit very slowly, through processes that have nothing to do with impacts. During the Apollo missions, astronauts deployed seismometers on the lunar surface to listen for moonquakes. These instruments operated for years, sending data back to Earth until they were finally turned off in 1977. What they revealed was surprising. The moon is seismically active, though far less so than Earth. Moonquakes fall into 4 main categories: deep moonquakes, shallow moonquakes, thermal moonquakes, and impact moonquakes. Deep moonquakes occur about 700 kilometers below the lunar surface, deep within the mantle. They are caused by tidal stresses from Earth's gravitational pull. As the moon orbits Earth, the tidal forces squeeze and stretch the lunar interior, creating stress that is periodically released in the form of moonquakes. Deep moonquakes are small, typically registering only about 2 on the Richter scale, and they occur in clusters at the same locations over and over again. The Apollo seismometers detected about 28 distinct source regions for deep moonquakes, and these quakes were found to follow a monthly pattern, occurring most frequently when the moon is closest to Earth, at perigee. Shallow moonquakes are much rarer, but much stronger. They occur closer to the surface, within the outer 100 kilometers of the lunar crust, and can register up to 5.5 on the Richter scale. That is strong enough to cause noticeable shaking and potentially damage structures. The cause of shallow moonquakes is not entirely understood, but they may be related to the cooling and contraction of the moon's interior, or to the reactivation of ancient faults left over from the moon's formation. Thermal moonquakes are caused by the expansion and contraction of the lunar crust, as it heats up during the day and cools down at night. These quakes are very small and occur near the surface, in the upper few meters of the regolith. Impact moonquakes are caused by meteorites striking the moon. These range from tiny tremors caused by micrometeorites to larger shocks from bigger impacts. The Apollo seismometers detected thousands of impact moonquakes over the years. One interesting feature of moonquakes is that they last much longer than earthquakes. On Earth, seismic waves from an earthquake die away within a minute or two, absorbed by the wet, fractured rock of Earth's crust. On the moon, seismic waves can reverberate for over an hour, ringing like a bell. This is because the moon's crust is dry, cold and rigid, with little internal friction to dampen the waves. The seismic data from the Apollo missions allowed scientists to map the moon's interior structure, confirming the presence of a crust, mantle, and small core. The data also showed that the moon is geologically inactive in the traditional sense. There is no volcanic activity, no plate tectonics, no ongoing mountain building. The moon is a cold, dead world, at least on geological timescales. However, the moon is not completely static. In recent years, high-resolution images from the Lunar Reconnaissance Orbiter have revealed fresh-looking features on the lunar surface, including lobate scarps, long, low cliffs created when the lunar crust is compressed, and buckles, pushing one block of rock up over another. These scarps can be hundreds of kilometers long and tens of meters high. The presence of these scarps suggests that the moon is slowly shrinking as its interior cools. Over the past few 100 million years, the moon may have contracted by about 100 meters in radius. That is a tiny amount, less than 1%, but it is enough to create stresses in the crust that occasionally relieve themselves in shallow moonquakes and the formation of lobate scarps. Some of these scarps appear to be very young, geologically speaking, with crisp, sharp features that have not been degraded by micrometeorite impacts. This suggests they may have formed within the last 50 million years, and possibly much more recently. The moon is still changing, still settling, still adjusting to the slow loss of internal heat. Another sign of recent activity is the presence of boulder tracks, trails left by rocks rolling down steep slopes. Some of these tracks are very young, cutting across older features, suggesting that the moon's surface is occasionally disturbed by small landslides or impacts. The discovery that the moon is not entirely inert has implications for future lunar exploration. If moonquakes are still occurring, particularly shallow moonquakes, they could pose a hazard to future lunar bases. Structures on the moon would need to be designed to withstand seismic shaking, just as buildings on Earth are designed to resist earthquakes. However, the risk is relatively small. Moonquakes are infrequent and generally weak. The moon is far more seismically quiet than Earth. But the fact that the moon is still active, even in small ways, is a reminder that no world is truly dead. Change happens everywhere, even if it happens very, very slowly. The moon's thin exosphere. When Apollo astronauts walked on the moon, they experienced what seemed like a perfect vacuum. There was no air to breathe, no wind to feel, no sound except what transmitted through their spacesuits via radio. For all practical purposes, the moon has no atmosphere. But strictly speaking, the moon does have an exosphere, an extremely thin, tenuous envelope of gas surrounding it. This exosphere is so insubstantial that calling it an atmosphere would be misleading. Its density is about 1 trillion times less than Earth's atmosphere at sea level. If you collected all the gas in the lunar exosphere, it would weigh only about 10,000 kilograms, roughly the mass of a large truck. The exosphere is composed primarily of helium, neon and argon, with trace amounts of sodium, potassium, hydrogen and other elements. These atoms do not behave like an atmosphere on Earth. They do not interact with each other or exert pressure. Instead, they follow ballistic trajectories like tiny satellites, rising above the surface and falling back down under the moon's weak gravity. The exosphere is constantly being replenished and lost. There are several sources of atoms. One source is the solar wind, the stream of charged particles flowing outward from the sun. When solar wind particles strike the lunar surface, they can knock atoms out of the soil in a process called sputtering. Some of these atoms are temporarily trapped in the exosphere before either escaping into space or falling back to the surface. Another source is outgassing from the lunar interior. Helium, in particular, is continuously produced by the decay of radioactive elements, like uranium and thorium in the lunar rocks. This helium slowly diffuses through the rock and is released into the exosphere. Micrometeorite impacts also contribute. When a micrometeorite strikes the surface, the energy of the impact vaporizes a small amount of material, releasing atoms into the exosphere. Finally, the solar wind itself contributes directly. Hydrogen atoms from the sun are implanted into the lunar soil and then slowly released back into the exosphere over time. The atoms in the exosphere do not last long. Some escape into space entirely, carried away by the solar wind or simply achieving enough velocity to exceed the moon's escape velocity. Others fall back to the surface and are either re-emitted or absorbed permanently by the soil. The average lifetime of an atom in the exosphere is only a few weeks to a few months. One of the most interesting features of the lunar exosphere is the sodium tail. Sodium atoms, when struck by sunlight, absorb energy and re-emit it as a yellow glow. This creates a faint tail of glowing sodium that streams away from the moon in the direction opposite the sun, much like a comet's tail. The sodium tail can be hundreds of thousands of kilometers long, and it can be detected from Earth using specialized telescopes. The existence and properties of the lunar exosphere have been studied by several spacecraft, including the Lunar Atmosphere and Dust Environment Explorer, LADE, which orbited the moon from 2013 to 2014. LADE carried instruments to measure the composition and density of the exosphere and to study the behavior of dust in the lunar environment. The exosphere varies with time and location. It is denser on the day side of the moon, where solar wind and solar radiation are more intense, and thinner on the night side. It also varies with the moon's position in its orbit. When the moon passes through Earth's magnetotail, the region of space where Earth's magnetic field is stretched out by the solar wind, the exosphere is partially shielded from the solar wind, and its composition changes. The lunar exosphere is also affected by meteor showers. When Earth passes through debris left behind by a comet, creating meteor showers like the Perseids or Leonids, the moon is also bombarded by this debris. The increased rate of micrometeorite impacts temporarily thickens the exosphere and changes its composition as more material is vaporized and ejected. Despite its thinness, the exosphere has practical implications for lunar exploration. Astronauts and equipment on the moon are exposed to this tenuous gas, and some of the atoms in the exosphere are ionized by solar radiation, creating a very weak electrical charge on the lunar surface. This charge can cause lunar dust to stick to surfaces, including spacesuits and equipment, a problem that Apollo astronauts encountered. The fine, abrasive dust clung to everything and was difficult to remove. Future lunar missions will need to account for the exosphere and the dust environment it creates. Engineers are developing new materials and techniques to minimize dust adhesion and to protect equipment from the harsh conditions on the lunar surface. The moon's exosphere is a reminder that even in the most barren environments, processes are at work, atoms are moving, and change is happening. It may not be an atmosphere in the traditional sense, but it is a dynamic system, shaped by the interplay of sunlight, solar wind, and the moon's surface. Future of the moon and closing. The moon is not finished with us, and we are not finished with it. After more than 50 years since the last human footsteps left their mark on the lunar surface, humanity is preparing to return. NASA's Artemis program aims to land astronauts on the moon again, possibly as soon as 2027 or 2028, with the goal of establishing a sustained presence. Unlike Apollo, which was focused on demonstrating technological superiority and planting flags, Artemis is intended to lay the groundwork for long-term exploration and utilization of the moon. The Artemis missions will land near the moon's south pole, a region of intense scientific interest. The permanently shadowed craters in this region are believed to contain significant deposits of water ice, which could be mined and processed to provide drinking water, oxygen, and rocket fuel for future missions. The poles also offer locations with near-continuous sunlight on crater rims and mountain peaks, ideal for solar power generation. Artemis will include the first woman and the first person of color to walk on the moon, broadening the diversity of human exploration. It will also involve international partners, including the European Space Agency, the Japan Aerospace Exploration Agency, and the Canadian Space Agency, as well as commercial companies developing lunar landers and other technologies. Beyond Artemis, there are plans for lunar gateways, small space stations in orbit around the moon that could serve as staging points for surface missions and deep space exploration. Companies and governments around the world are developing plans for lunar bases, research stations, and even tourism. The moon is also seen as a stepping stone to Mars and beyond. Many of the technologies and techniques needed for long-duration missions to Mars, such as life support systems, in-situ resource utilization, and radiation shielding, can be tested and refined on the moon, which is only 3 days away and allows for relatively quick abort and rescue if something goes wrong. But even without human intervention, the moon's story continues. The moon will keep receding from Earth at about 3.8 centimeters per year. Over the next billion years, it will move tens of thousands of kilometers farther away. Earth's days will continue to lengthen, and the tides will gradually weaken. In about 5 billion years, the sun will exhaust the hydrogen fuel in its core, and begin to swell into a red giant. It will grow hundreds of times larger, possibly engulfing the inner planets, including Earth and the Moon. If the Earth-Moon system survives this expansion, it will be a scorched, airless wasteland, bathed in the dim red glow of a dying star. But until then, the Moon will continue its patient orbit, pulling on the oceans, stabilizing our climate, lighting our nights. It will remain a destination for human curiosity, a symbol of exploration, and a reminder of where we come from and where we might go. The Moon has been with Earth for more than 4 billion years. It has witnessed the rise of the continents, the birth of the oceans, the emergence of life, and the evolution of intelligence. It has seen dinosaurs come and go, ice ages advance and retreat, and civilizations rise and fall. It was there when the first humans looked up and wondered what it was, and it will be there when the last humans, if there are any, take their final steps on its dusty surface. The Moon is our companion, our anchor, and our first step into the cosmos. It is a world of extremes and mysteries, of ancient rocks and future possibilities. It is a place we have touched, and a place that has touched us, shaping our planet and our destiny in ways we are only beginning to understand. So tonight, as you drift off to sleep, perhaps you will look up at the Moon, if it is visible in your sky. And perhaps you will think about its violent birth, its cratered face, its slow waltz with Earth, and the footprints still preserved in its dust from half a century ago. Perhaps you will think about the future missions, the discoveries yet to come, and the possibility that one day humans will live and work on that distant silver world. The Moon is always there, a quiet presence in the night, a reminder that we are part of something larger, something ancient and ongoing, a cosmic dance of gravity and time. If tonight's journey helped you drift off into peaceful sleep, and if you'd like to join us again for more explorations of the cosmos, please consider liking this video and subscribing to the channel. It helps others find their way here too, one curious mind at a time. Thank you for listening and good night. Sleep well beneath the light of the Moon.